All right, so now we're gonna, this is gonna be a really short one. We're gonna do just a couple of simple problems, and I'm gonna do an extended one on various interest rates, and we're gonna use old techniques. All right, so just a very simple idea of how do we do population growth. Um, so say in a small country, you have a population that grows according to this model. So you have population at time t, where t, right, is years since 2000, 2000, right? You have 2.4 million times e raised to the power 0.03 times t, right? Now, this 0.03 is a rate. It's often denoted by r. Okay, now you need to be told what the units are here. This is not something that you can completely, intuit just from this form. So you're told that PT is measured in millions, and the time goes like this. So basically, looking at this, you immediately understand that what corresponds to the year 2000 is when t is equal to 0. So this is like your origin of time. 2000 is when they start counting. Okay, so here's like basic questions: is what is the population in the year 2000, and what is the population in the year 2020? Okay, so now that we've introduced this, I'm gonna park myself out here somewhere, maybe out here. Okay, there we go. Okay, so now this is very simple. Okay, now that we realize that time, when time is 0, we can just plug this t equal to 0 here. This is going to become 1. I have 2.4 millions in the year 2000. Okay, that's basically the parameters of the problem. Now, in the year 2020, t is 20. So I just take 20, plug it in here, evaluate, and what do I get? You need a calculator for this, but it's about 4.4 million. Now this is very simple. Of course, we could be asked is when, for example, what year will the population double, okay, be twice the original amount? Okay, so in what year can they expect the population to double? So what you're looking at, you know that in double what? Double what it was in 2000. So this is asking you, so you need to find t, okay? Okay, so now I'm going to ask another question. So find when population doubles. Okay. So basically what I need is, I want to know that t, okay, such that p of t0 is equal to twice, okay, what it was, so 4.8 million, okay? How do I do this? Well, I just equate it to this, 2.4. I have E 2.0 3t, okay? And then what do? Well, for starters, usually I would just divide, right? I would divide by 2.4, and I would say, oh, well, what I'm getting here is something like this. And notice this is going to be like always. So I have 2 is equal to e to the E0 3t. Does this ring any bell? Okay. No, look, it doesn't matter what I started with. It doesn't matter what I ended up with. All that matters is it's doubled, right? So basically, all the doubling questions are going to have this shape. Okay. So then now, how do I get this? Well, I can take just the natural log of both sides. I am going to have 0.03 t is going to equal to the natural log of 2. Okay, and so the time is going to be ln of 2 divided by 0.03. And if your calculator is malfunctioning, this is an acceptable answer. Okay, but if it's not, well, it's really, you should be computing it. So what is ln of 2? Well, it's going to be a little bit less than 1 in, really close to 1, but a little bit less. So we're going to be multiplying this by essentially 30, right? So the rate is 0.03, and we're going to be, so that's the same as dividing by this, dividing by 3/10, 3/100 is the same as multiplying by 100 and dividing by 3, which is essentially like multiplying by 33.333. But, so roughly, time is about 30 years or so. So that's, just in the ballpark, so what you should be expecting to see from your calculator. This also makes sense because I know in 20 years it doesn't quite double. Okay, so that's sort of like kind of a way of eyeballing things. Right, so now let's move on to the next problem. Okay, next problem comes out of carbon dating. Right, so carbon dating is this very interesting process based on this kind of idea that there's a certain concentration of radioactive carbon in the atmosphere and therefore in all the living things that ingest it. Well, most living things, I should say. It's not completely true. And then, well, once the living thing dies, it stops consuming new carbon 14, and the amount of carbon 14 starts decaying, right? And then, so we have this model of decay. Notice that this is a decreasing function, right? Since r is negative, this is really the same as something like this. So a is really the same as 3.6. Yes. Okay, and something like 1 over e, right? 1 over e, and then, plus, so 1.21 times 10 to the minus 4 times time. Okay, I'm only putting this here for illustration because you already know that when we are taking exponential of something else with a base that's less than 1, we actually have a decreasing function. Yeah, so that's really the only thing you kind of need to know about this. All right, so the question is, what is the initial amount and what is the amount present after 10,000 years? Okay, well, the initial amount is this. There's no change. That's your initial amount. So that corresponds to t being 0. Yeah. And so we raise e to the power 0, get 1, and so that's your initial amount, as always. Okay. So now, how do you compute, though, a of 10,000? Okay, I think I have all this typed out. I don't know why I'm writing it. I got carried away, sorry. So I have 10,000, right? Well, there's only one thing to note here, is that we really need to compute r times t. And r is like this, minus, okay, 0.000 0, 1. So when I multiply with 10 to the minus 4, means I have to move the decimal point 4 times over, right? Once, then I write another 0 twice, another 0 3, and last 0 4, and that corresponds to this. Okay, and then the rest of the numbers. So that's what I have. But I need to multiply with 10,000. And 10,000, well, has 4 zeros itself, right? So I'm just going to be moving everything back. So this is literally corresponding to minus 1.21. Okay. And that's what you see here. This is R times T. Okay. Now you'll need your calculators for this. 3.6 times E raised to this power is going to get you 1.1 gram. Right. So the next problem is going to play this kind of very similar game but backwards. So now we're going to estimate the age of the fossil. Okay, so we now we have exactly the same model, and now we know that there's only half a gram left. So we want to know how old is the fossil. So what we have is this. Okay, this, right, equals 0.5, half a gram, right? So of course, I mean, there's a very, like, a great deal different number of different things I could do at this point, but I could just go straight forward. I could just take logarithm, and here I have log base 10, but you could take natural logarithms. It doesn't change anything. Log of this product is a sum, right? Log of an exponential is just going to be this, okay? And log of half is going to be log of half. Now, I just subtract this logarithm from both sides, and I end up, well, have to take t, that is, okay, now don't forget that there's this minus. Uh-oh, I think there are too many minus signs. I have too many minus signs in there. So this is plus. This is meant to be this minus sign. There's only one of them. Okay, so there's only one minus sign, but you will end up with this number is actually going to be negative, right? Because 0.5 is less than 1. So log base 10 is going to, of 1 is going to give you 0. Anything less than 1 is going to be negative. So that's a negative number, and that's a negative number, and you will end up with dividing this by a negative number, so you'll end up with a positive number, right? Did I say how much? So it says perhaps should be rounded, you know, to a nearest year, so about 16,315 years. Okay. So this is how you play this game backwards. Okay. Now, in the very same kind of vein, you can compute the number of years it takes to pay off a loan. So when you have this amortization formula, it takes this shape. I will discuss with you in great detail how this formula is derived, but right now I just want you to practice using it. So if I is the interest rate, right? So we have the it's the per period interest rate, right? So we have 8% annual, and we have 12 months, and the interest is compounded monthly. Okay, we know are the monthly payments, right? Okay, are equal to the premium, right, times the interest rate divided by this. Okay, that's a kind of complicated formula. It's a little bit unmotivated here, but still, we can use it to find what we want. Okay, how do we do this? Well, we just plug everything in. We know what I is. Okay. We know that this is 1200. We know that this is 90,000. Okay, now we just simply solve this as an equation. Okay. Now, if I take 90,000 and I divide it by 12 and then multiply with 0.8, I do believe that I'll get something like 600. Okay, so this is just the result, and then I'm going to multiply this, the denominator, to both sides. Okay, and now at this point I have this kind of an expression. Well, I really should divide by 1200 and get a half. Okay, now so I have 1 minus this equals a half. It's still kind of complicated, so what I'm going to do is I'm going to just subtract half from both sides and add this to both sides, so I'm going to have something simpler looking. And then, now at this point, only at this point am I going to take my logarithms. So I have ln of 1/2 is equal to minus 12t times ln of 1.005. Right, so, okay, now if you plug this in, okay, so then minus 12t, right, has to be the ratio of two natural logs. Okay, and then t has to be the ratio divided by minus 12. Okay, so if you compute, it ends up being about 8.6932 years. This doesn't make a whole lot of sense to have 1,000 digits, this kind of accuracy in a year. So, and with their interest being compounded monthly, right? I would say that it only makes sense to do about this. So I would say 8.7 years. Okay, so that is really a much better answer. 8.7 years. Okay, so if you turn this into the number of months, you would realize that this would amount to about 8 years and 8 months. Okay, so thank you, and I'll see you next time with this kind of last extended discussion from exponentials and logarithms. Will be our last lecture about the various kinds of interest rates.